So, like we are discussing just now, we have to verify the different timing requirements of our designs, and they matter a lot. Once the functionality has been proven to be good at the RTL level, the next big thing for us is to make sure that this functionality will still be valid considering the different timing aspects of the design. And a combination of both is going to give us a silicon which works well. So functionality and timing. So that's why I strongly think always that your design verification and your static timing analysis sign off are the key things to prove to you that you're ready for silicon. Your design verification is going to tell you that your functionality is good to go. And your STA person is going to tell you that your timing aspect is good to go. These two are the key aspects, and the more amount of detail we put into these two aspects, the more accurate our silicon will come out to be. So always focus on these two aspects with great purpose. So we just validate how they operate at a certain rated frequency and constraints, to be very simple about it. And why is it called static in the first place? It is called static because there is no vector that we are putting in. See, what is timing? Timing is, suppose a signal is changing from 0 to 1 at a particular point. Will it reach a destination point within a certain time? Now, how will you prove that? How will you analyze that? Only way is to pass a signal like that and then see the traversed path and calculate the time. For that, you need to have vectors generally, right? But static timing analysis is smart to actually create, pass these signals or, create these transitions inherently in the tool. And you're not providing any kind of a vector from outside. All you're trying to say is, this is my timing requirement, go and analyze. So it statically passes all that. That is to say, it represents the entire structure of the design and then approaches it what is known as topographically. That is point A to point B to point C to point D kind of a thing. And from the library, it picks up the values that correspond between point A to point B to point C, so on and so forth, and comes up with a number for you. All right, so no data inputs are required, and that is what makes it. So it's a vectorless topographical analysis of the circuit. So look at this picture here. Now you have a AND gate or an AND gate here, couple of inverters, and then going to another AND gate kind of structure with inverted inputs. Now there are multiple paths possible here. So the static timing analysis tool understands these paths. That is, for the first AND gate, there is a path from one of the inputs to outputs, another input to output. Again, from this common point, the path can go through the upper inverter, path can go through the lower inverter. Again, at the destination gate here, at the third gate here, input to output possibilities are there. So if you look at the paths, there are multiple paths possible. Like if you start at the lower gate here to this guy, and possibly through this inverter and through this and to output, or through this inverter and to output. So there are multiple paths possible if you observe here. Now, one important point which we have already realized is the delay between the input of any gate to the output differs from another input of the same gate to the output. We cannot expect the same amount of delay from the inputs, though they belong to the same gate. So that adds an extra variation for you in terms of which is the longest path kind of a thing. Eventually, you will know that one of the paths will end up being the longest, while the other path and one of the paths ends up being the shortest, right? So that's what this is trying to represent for you, the possibility that the path from upper input to the output of the first gate is a longer path, let us say, However, the upper inverter is a shorter path compared to this guy. And then let us say, for example, the input to output of this gate is, let's say, the same value. It's just an example. So you will find that there is a certain variation possible, even though you're looking at simply 4 gates here. I mean, 3 levels of delay here. Static timing analysis has the ability to look through all the possible paths in your design like this. And it comes up with what is the worst case path between point A to point B. So that's what makes this tool exhaustive, because it has the ability to look through all the possible paths. Now, as opposed to, let us say you're trying to run a simulation, your simulation may actually toggle just this vector, this point. It may not be toggling this point at all. So you're limited by the ability of your simulation to toggle a node to see what is the variation because of that, variation in delay. If a node is not toggled in a simulation, let us say I'm talking about your regular functional simulations, if a node is not toggled, then you would definitely not know the impact on timing because of a signal flowing through that node, right? So to depend completely on some kind of vectors in order to analyze a million gate design is a big no-no. It's very difficult actually. It is limited by our ability to toggle all the paths. And that is where the static timing analysis comes and bridges the gap, where it guarantees that I will look at all the paths for you. And it's going to come back and comprehensively give us an idea about, what are the longest paths and shortest paths and so on and so forth, and optimize it or provide you analysis and data for taking decisions. See, STA tool is a pure analysis tool. Don't forget that. It is not it doesn't translate a netlist or it doesn't change the netlist and all that. It won't do those kind of things for you, but it gives you complete data for analysis and take decisions about how to move forward, right? So dynamic timing analysis is another aspect where you are trying to actually simulate your circuit with vectors, that is to say with your test cases. Now, this particular method has its limitation like we discussed. So dynamic timing analysis, you're trying to pass patterns through some codes and then you're seeing the response, and then you're seeing if the response is within a certain time duration that you would expect. So that's going to come back and then give you violations for sure. It is going to, when you run a simulation by passing patterns on the gate level netlist, the tool is going to come back and say there have been violations on hold, setup or whatever, depending on the constraints you have put in your network. So that is definitely a possibility. However, it is limited and greatly limited by the ability to generate these patterns. And so dynamic timing analysis as a method of sign-off is a improbable aspect for us today. So just capturing between static timing analysis and dynamic timing analysis. So static timing analysis doesn't need any inputs. Dynamic timing analysis depends on the input vectors. And of course, both are not alternatives to each other. Each of them accomplishes a certain part of the circuit or certain aspect of the circuit. Now, STA can only be run on a synchronous design. Okay. As long as there are asynchronous paths in the design, STA is trying to put a false path on them, right? Now, what about the timing requirements or functional time requirements on your asynchronous paths? Now, that is where the dynamic timing analysis plays a very big role in giving us an idea about it. So, it is very much suitable for designs where you have a lot of asynchronous paths, which you need to see how well they are behaving or how well they are passing from one part of the circuit to another. And also it is very suitable for designs where multiple clock domain crossings happen. And assuming that all these clock domains are asynchronous to each other, then some kind of a dynamic timing analysis may be required for those kind of designs, focused on the boundaries. All right. So So as an engineer, you need to understand and appreciate where each aspect plays a strong role and what are the gaps in each of the approaches, STA and DTA. So today's designs with very complex circuits and densities, running dynamic timing analysis simulations is pretty much limited or rare. But they have compensated it with other mechanisms, like you have CDC, like clock domain crossing analysis that is done, which takes care of your asynchronous versus synchronous domains and how signals are moving, whether it has been addressed or not, kind of a thing. Formal verification, which guarantees you functionality, and static timing analysis, which takes care of all your synchronous parts of the design. So that has become one of the reasonable alternatives for running dynamic timing analysis, because dynamic timing analysis consumes a lot of time to simulate and verify, and it is also limited, like we have been discussing again and again, by your ability of your vectors, how good your vectors are in the first place. STA is much faster. Now, how does STA fit in your overall flow? Right, we know RTL design, simulations, logic synthesis we have done, and after we synthesize, we do one round of STA. And this STA we know doesn't have any kind of good data with respect to the routes. So clock tree is ideal there. We have not done any kind of a clock tree balancing there. And then after we do placement, clock tree synthesis, and then routing, that is where we again come back and do the STA. At this point, it is with the real accurate data, which has two important things. Here we get the clock tree, and we also get the routing information of different signals. Clock tree, like we have covered in some earlier classes, clock tree is all about buffering your clock. See, your clock has got a huge fan out. Right? If you were to think about it, the two signals which will have a heavy fan out in your design are really the clock and the reset. Because the clock goes to every flip-flop in your design. Right? So suppose your design has got 1000 flip-flops. Your clock pin is seeing a fan out of 1000. And imagine the kind of load that is sitting on a line with 1000 endpoints. So obviously the signal flowing through such load will transition very slowly unless you do something special to address its load requirements. So that is where we build what is known as a tree, where you have a buffer tree typically, where you have one buffer feeding something like 6 buffers, let us say, each of these 6 buffers feeding another 6 buffers, and so on and so forth. Like we build a tree of different levels, and that is called a clock tree synthesis. Okay, and so that information is very crucial, because that is going to tell you how much is the latency that we have achieved for ensuring your clock transitions are clean at different parts of the design. So that information, along with the real routing information, that is how long are your routes, and so what are the parasitics associated with them, the resistance and capacitance values. So all this information which we get from the physical design has to go into the STA tool, and then we do an analysis which is a lot more closer to the real situation of your design.